Hello everyone. Welcome to our presentation. This paper is authored by Aldemar Sequeira, Perzio Bajos and Josué Lubauki, from the University of Campinas. This work investigates the dynamic response of an elastic, partially buried strip footing under vertical and horizontal external time harmonic loads. The footing is modeled as a two-dimensional embedded rectangle discretized by plane strain isoparametric finite elements. The soil is a two-dimensional, isotropic, viscoelastic half-space modeled through an indirect boundary element formulation. Solutions for this medium are obtained by superposition of Green's functions for buried loads. Direct kinematic compatibility and equilibrium conditions are used to couple the finite element mesh to the boundary element mesh, assuming perfectly bonded contact at the foundation soil interface. The effect of foundation embedment and elastic properties on the dynamic behavior of the foundation is illustrated with selected numerical examples. Consider an elastic, isotropic strip footing with these properties, with infinite length in the y direction and a rectangular cross-section of width 2a and height b. This structure is embedded in a two-dimensional homogeneous, isotropic, viscoelastic half-space, with these properties. We considered a plane strain case, and that the structure is perfectly bonded to the soil throughout the structure-soil interface. Time harmonic horizontal and vertical loads of magnitude fx and fz can be applied anywhere in the domain of the structure in terms of nodal equivalence. The structure is modeled with linear elastic, four-noded isoparametric quadrilateral finite elements, with 2 degrees of freedom per node. The elemental stiffness and mass matrices are given by equations 1 and 2, where B is the strain displacement transformation matrix, C is the constitutive matrix for a plane strain case, J is the Jacobian operator, and N is the shape function vector. The dynamic stiffness matrix of the structure is given by this, in which Kg and Mg are the global stiffness and mass matrices of the structure obtained through the classical finite element assembly scheme, and omega is the applied load frequency. An indirect boundary element method formulation is used to model the soil. This procedure consists in connecting the displacement and tractions at discrete points in the half-space through a set of fictitious loads. These loads must satisfy prescribed continuity and equilibrium conditions given at the discrete points. The soil foundation contact interface is discretized in NS constant boundary elements and, for the whole interface, the displacements and tractions are given by this and this, in which Q is the vector of fictitious loads, and U and T are the matrices of displacement and traction influence functions, which are non-singular Green's functions. In this paper, we have used stress and displacement influence functions developed by Bajos for time harmonic loads applied inside the half-space. The traction influence functions are given by the product between the stress influence functions tensor and the boundary's normal vector. Influence functions for loads that are uniformly distributed in the vertical direction are used for elements placed at the side walls of the interface, while influence functions for loads that are uniformly distributed in the horizontal direction are used for elements at the bottom wall. The general expression for the displacement and stress inside the half-space are given in terms of Fourier integrals that must be evaluated numerically. The terms Uij bar and sigma ijk bar are functions of the elastic constants, and of the depth and frequency of the applied load. The integrands of these equations are characterized with two distinct regions, a portion with the presence of singularities and a portion with an oscillatory decaying behavior. In the present work, the singularities problem is addressed by incorporating a small hysteretic damping into the material constants. This strategy smooths out the singularities and makes them integrable by ordinary adaptive quadratures. The oscillatory portion is evaluated with an adaptive Gaussian quadrature. For a detailed discussion of the influence functions and their numeric evaluation, please refer to Bajos' article. The structure is discretized such that there is one finite element coupled to one boundary element at the interface. This coupling is established by imposing equilibrium and continuity conditions at corresponding elements' interface. Each finite element is considered to be perfectly bonded to its corresponding boundary element. The influence of the presence of the soil is incorporated as a set of equivalent nodal contact forces Fs acting on the finite elements at the foundation soil interface. The dynamic equation of motion for the structure is given by this. Notice that the boundary and finite elements have different orders of approximation, so the number of nodes in the boundary element mesh is incompatible with those of the finite element mesh. The vector of contact forces is related to the vector of contact tractions through this linear transformation, in which A is a purely geometric transformation matrix that is responsible for correcting the incompatibility between the position of the finite and boundary element nodes. In view of this compatibilization, the equilibrium equation for the structure can be written as this. Continuity between the soil and the structure is imposed by writing the displacement of each boundary element in terms of its corresponding finite element equivalent nodal displacements. This can be obtained through this linear transformation. Please refer to our paper to see the expressions of transformation matrices A and D. This compatibilization yields this. Writing equations 6 and 7 as a single expression yields the equilibrium equation for the coupled foundation soil system. The solution of this system yields the displacements on nodes of the structure and the fictitious contact loads applied to the boundary elements at the interface. This section presents an analysis of the influence of an elastic strip footing stiffness and embedment depth on the dynamic response in contact tractions distribution at the foundation soil interface. Results are presented in terms of the normalized frequency and the normalized horizontal and vertical compliances, in which UI is the displacement measured at the centroid of the cross-section. All results consider a footing with Poisson ratio 0.3, and the soil is an isotropic half-space with these properties. In order to validate the present model, these figures show the vertical and horizontal compliances of a rigid, massless embedded footing. Different embedment ratios were considered, including that of a surface footing, approximated with the present model by setting an embedment ratio of 0.01. Rigid and massless properties can be obtained with the present model by making the structure much stiffer than the soil and with zero mass density. These results were compared with Israel and Ahmad and Baradwaj, showing a good agreement. This figure shows the influence of the soil structure stiffness ratio on the dynamic response of a massless embedded footing with embedment ratio 1. In these results, the external loads are applied at the centroid of the cross-section. These results show that stiffer foundations present significantly smaller kinematic responses. Notice that, for footings 100 times stiffer than the soil, the footing behaves like a rigid body. This figure shows the effect of the depth of embedment of the footing on its dynamic behavior, for different values of stiffness ratio. This example considers a footing with twice the mass density of the soil, and applied load with normalized frequency 1. Notice that, as the embedment ratio increases, the amplitude of the foundation's dynamic response drastically decreases, especially for stiffer foundations. For values of embedment ratio larger than 1, the influence of the depth of embedment of the footing on its dynamic response becomes negligible. This figure shows the influence of the depth of embedment of a rigid footing on the distribution of contact tractions at the bottom interface between soil and structure. The results are presented in terms of the normalized traction components acting at the interface between the bottom of the footing and the soil. The footing has twice the mass density of the soil. Notice that the amplitude of tractions decreases significantly with increases in the embedment ratio, especially for foundations under vertical loads. The sharp increase in the magnitude of the traction components toward the edge of the foundation is physically consistent. This paper presented a model of the time harmonic response of an infinite elastic strip footing partially buried in soil and subjected to external loads. An IBEM-FEM coupling scheme was proposed to model this foundation-soil interaction problem. The condition of perfect bonding between structure and soil was modeled by establishing continuity and equilibrium conditions throughout the soil-foundation interface. Results showed that the elastic properties and depth of embedment of the footing significantly affect its dynamic response. Thank you for watching this video. The author Aldemar Sequeira will be answering your questions now.